right, we're going to look at the last topic in section 5.3, which is an application of the fundamental of theorem of calculus. Here we have an equivalent version of the fundamental theorem of calculus, and the major difference is here we've got a derivative function, which we're going to integrate. And because these are inverse operations, when you integrate a derivative, you get the original function back again. And what this says is when you integrate the rate function, you're finding the difference, the change, because we're subtracting here, between function values. So you're finding an amount of change. So I always taught my students the phrase integrate the rate. It's nice because it rhymes. When you integrate the rate, you get an amount of change. So this is how we have a lot of different applications then, where if you know the rate at which something is happening, you can calculate how much it's going to change over a time period. So in this example 5 from your textbook, it says demand for electricity varies predictably over the course of a day. Drawing on experience, engineers in a small town use the formula, and then you have this rate formula, which is quite a mouthful. And it says to model the town's typical rate of consumption in megawatts T hours after midnight. So on this axis, we have hours after midnight. And on the other axis, we have the rate, which is measured in megawatts. Now, if you're wondering how is that a rate, because rates are something per something, just so you know, a watt is a unit of measure that's equivalent to joules per second. So a watt in and of itself is a rate, okay? You don't really need to know that to do this, but if you're wondering why I didn't put like megawatts per hour there, that's why. Okay, the first question says, is the model reasonable? So if you look at the model at 0 hours, right at midnight, you have a certain level of consumption. This is a positive 2, kind of looks like negative, but it's positive 2 megawatts. And it increases up to 6 a.m. Then it dips down towards noon, back up towards 6 p.m., and then tapers off through the evening. In pandemic times, this, you could argue, isn't entirely accurate because when people are staying home all day, the curve might actually be something more like this, where you reach your energy usage and you kind of plateau there because you're staying home all day. But if we assume normal pre-pandemic behavior, most people are home, get ready in the morning, leave, go to work, and come back. So I would say that for pre-pandemic times, yes, this does make sense. So you should be able to read a graph and interpret it. What does the shaded area represent? Well, remember, a shaded area is an integral. And the integral here is going from 0 to 24 hours after midnight. And it's the integral for the function r of t dt. Okay? Now, like we saw above, when you integrate a rate, you get an amount of change. So the shaded area here represents the amount of change in energy usage over 24 hours. Integrate the rate and you get an amount. And then the last part, part C, says, what is the amount of electricity consumed in a day according to this model? This requires an integration technique you haven't learned yet. So at this point, the book takes you through saying, well, okay, we're going to have to take the integral from 0 to 24 of our rate function, which is this whole thing. And then they basically are asking you to kind of guess what the antiderivative for this would be, sort of knowing, kind of thinking backwards about, okay, well, how would you take a derivative and get this? I think it's a little unrealistic to think you would be able to do that at this point. So I will just tell you, 4, you should know from the work we've already done that that would come from taking the derivative of 4t. Remember, t's are variable here. And then the book does just give you the correct antiderivative for the rest. And they indicate like you should be able to look at this and understand how if you took the derivative of this, you would come up with what's above it. It involves using the chain rule, which we're going to be reviewing shortly. And then you're supposed to, substitute the values of 24 and 0 into this to get your actual numerical answer. There's nothing hard about doing that substitution. It's just a whole lot to type into a calculator. First, you go through and put 24 in place of all of the t's. Then you go in and put 0 in place of all of the t's. You subtract those numbers. And cutting to the chase, you get approximately 95.781. And the proper units here is what's known as a megawatt hour. Okay, and I'm not expecting you to know the units here either. The whole point is to have you see that apparently the change in energy usage over the course of one day ends up being 95 megawatt hours, and that from the rate we get the amount of change. All right, so that's a nice application when working with integrals.